All right, so for question number 2, for each of the scientists, describe his invention, the type of energy the inventor was able to produce, and how it was produced. Okay, Oersted, what did he find? Nick? Okay, so he had the compass and the wire contraption. All right, so he found that when current went through a wire, which is what kind of energy? Electrical, could produce magnetic effects. Essentially, it was the groundwork for the first electromagnet. Okay, when he found that electricity could produce magnetic effects, okay, you could develop then from that an electromagnet. Very simply, it's a piece of iron wrapped in copper wire, okay, where there's current going through the wire. Okay, you can induce a magnetic field using that, and you have an electromagnet. Okay, okay, for Faraday, what did he discover? Pardon me? Yeah, first generator. He found that the relationship Oersted found could go the other way, okay, that a magnet could produce movement of electrons, that is an electric current, okay, so that developed the first electric generator. Okay, what about Seebeck? Yeah, he had the thermocouple. He found that you could convert heat directly into electricity, although it's not very efficient. All right, Edison. Yeah, he's the light bulb guy. Okay, very famous for being asked by a journalist at one point, did you ever, at any point, did you consider yourself a failure since you tried to make a light bulb like 600 times and failed? And he said, no, I found out 600 ways how not to make a light bulb. Totally a glass half full kind of guy. Okay, what about Volta? What did he invent? Hmm. I have no idea. It would seem unlikely given that the tungsten would eventually just weaken. I mean, that's why light bulbs burn out. The tungsten just weakens and breaks. Or the seal for the light bulb breaks and then the tungsten ignites. Like inside a true light bulb is a vacuum. You can't have any flammable gas in there, right? Okay, and then Volta made the first battery. Okay, so chemical energy into electrical energy. Okay, so stated practical use of the invention today. Well, electromagnet for Oersted, making generators for Faraday. Okay, for Seebeck, we talked about how that can be used to help charge batteries in hybrid cars or as a circuit breaker. Okay, Edison, obviously, we still, light bulbs still used for the same thing. And Volta, yeah, we still use batteries for the same thing as we did before. All right, what's the difference between nuclear fusion and nuclear fission? Right. Okay. So fusion involves the forcing together of many atoms, 2 or more. Okay. Whereas fission involves the breaking of a single atom into smaller parts. Okay. What are they? How are they similar? They both harness energy stored within the structure of the atom, within the nucleus in particular of the atom. Anytime we change the nucleus, energy is going to be released. Okay. Modern theory of the source of energy for the sun. Well, we just talked about it. Nuclear fusion. Okay, the immense gravitational pull of the sun is so strong that it can actually force hydrogen atoms together to form helium. Okay, number 9. Okay, describing the contributions the following people made. Okay, so Sadi Carnot, what did he do? We didn't talk much about him. Exactly. He found that you can only convert thermal energy into mechanical energy if you are looking at going from a hot object to a cold object. You have to follow the flow or the rules or laws of thermodynamics if you're going to perform any energy conversion. Okay. All right. What about Young? What about James Young? Didn't talk much about him either, but he's in there. I want to find where he was here. Where was he? Sorry, it's James Thomas Young. Is that what was confusing everybody? Not being able to find James. It says Thomas here. It should be James Thomas Young. Right. Okay, so we got he linked that mechanical energy is essentially the sum of kinetic and potential. Okay, so that's essentially his work led to the definition of energy that we currently use. Okay, okay, and then we got Rumford. Rumford was the Cannon guy, okay, who discovered that mechanical energy can turn into heat, okay, or into thermal energy. He was the one who had the kettles boiling on top of the cannons while they were being bored. Okay, number 12, okay, in the following situations, identify the major form of energy involved. Okay, an antacid tablet is placed in a glass of water and the tablet starts to bubble. Plop, plop, fizz, fizz. What kind of energy would that be? Chemical, yeah, okay. It's a chemical reaction. It releases the carbon dioxide and whatever else that's in the antacid tablets. Okay, for B, a fluorescent dial on a wristwatch glows. Something's glowing, it's giving off light energy. Okay, a downhill skier begins to ski down the slope with increasing speed. Yeah, I would say mechanical would probably be the best answer, although you could make an argument if you're just talking about kinetic. Okay, but mechanical I think would be the most accurate. For D, a tingling sensation is felt on the tongue when it's touched to the terminals of a 9-volt battery. That's electrical. Anyone ever do that before? Okay, yeah. I mean, 9-volt battery, okay. Anything bigger than that, don't do it. Okay? Or you're going to have like marks on both sides of your tongue, right? You don't want to do that. Like car battery, don't. Yeah, don't take booster cables and go, is this battery okay? It'll be fine. You won't. Okay? All right. The inside of a car gets extremely warm if the car is left in the sunshine. Yeah, I'd say thermal, but I'd also say you could look at light being the origin of that energy, okay? And like it comes through the glass and you essentially get the greenhouse effect going. The wavelength of the light is changed as it passes through the glass, bounces around inside the car but can't escape, okay? That kind of thing. All right, F, a seagull lifts a clam high above the beach. Okay, I'd say potentially you can make an argument for, but potential is a form of mechanical. Okay, so I would say both would be correct there. Okay, a compass needle is held over the surface of the earth and points north. Magnetic, yep. Okay, describe an appliance or machine that for its operation requires the following forms of energy. Well, chemical is easy. Basically anything you have to put fuel in, right? So you could say, a car, a lawnmower, a snowblower, a barbecue, okay, whatever. For B, light. Yeah, solar panels, okay, anything like that. Even a thermal heater, okay, like a solar heater. Those ones where you put like the black tubing out in the sun and the water circulates through the black tubing and heats up. Okay, that's the same thing. It would require light. Okay, for heat, anything that requires heat, I'd say anything that uses a thermocouple, okay, would require heat to work. Electrical energy, anything you plug into the wall. Right, you've got a pretty wide range of things to choose from for that. And then magnetic energy, compass, yeah. Okay, describe an appliance or machine that produces the following forms of energy. So chemical energy. Yeah, a car has an alternator in it. It can be used to generate electricity. Okay, or not uses. This is produces. Produces chemical energy. Sorry. I would say a refinery, okay, like an oil and gas refinery would produce chemical energy. Okay, I would also say, even though it doesn't really, it says appliance or machine, plant isn't really an appliance or machine, but it certainly produces chemical energy. Glow stick is taking chemical energy and turning it into light. It is a chemical reaction that produces light. Yeah. All right, and then anything that produces light, well, okay, a light bulb. I'm going to go with that. That's the simple, easy answer. Okay, produces thermal energy. Okay, putting in brakes on a car, a heater, toaster, yeah, okay, hair dryer, yeah, okay. Electrical, battery, okay. Magnetic, a magnet, yeah, okay. Yeah, anything like that. Even or a transmitter of any kind also produces magnetic energy. Okay, we're transmitting electromagnetic waves, so your cell phone, okay, also does that. Okay, so that'll answer all of those. Okay, any questions on any of those? Okay, that stuff might come up on quizzes. Some of it could be game for a multiple choice question on a test or something like that. There certainly wouldn't be any like long written response items about the contributions of Sadi Carnot to energy or anything like that. All right, so we got to talk about the laws of thermodynamics next. So this is lesson 2 in your notes package. Okay, the laws of thermodynamics govern the movement of energy in systems. Okay, so we need to look at first off the kinds of systems and then look at how energy flows through them. So the laws of thermodynamics, basically there's 2 that we need to worry about. Okay, the first law of thermodynamics is the law of conservation of energy. Okay, energy can't be created, it can't be destroyed. That's the first law. Okay. The second law of thermodynamics talks about the flow of energy, okay, from one object to another. And energy always flows from hot to cold, high energy to low energy. That is always the flow of energy. Okay, so in thermodynamics, energy always flows from hot to cold. Okay, so anything that we use is governed by certain physical laws. Okay, they describe the relationship between work and energy transformations, but they focus on one type of energy, and that's heat. Okay, well, thermal energy in particular. Okay. We had talked about mostly mechanical energy before. Okay, so now we need to look at kind of more the thermal part of it. So the first thing we need to know is what's a system? Okay, and this is an important definition going forward in all physics courses. A system is a set of interconnected parts. Okay, so if I was, let's say, hauling a heavy weight up a ramp using a rope and a pulley, okay, the rope, myself, the pulley, the mast, the ramp would all be part of a system. Okay, those are all interconnected parts. Okay. When we're looking at energy transfers, the system is the object or objects involved, okay, in the transfer of energy. Right, so all those parts are connected. They can transfer energy easily to each other. Right. When we're talking about systems and energy, though, oftentimes systems can lose energy to the stuff around them. What do we call the things that are around us? No, like this room would be considered your surroundings, exactly, because there's systems, that's the parts, there's the surroundings, that's everything around the system. Okay, they're not necessarily connected to the system, but they're around the system, and energy may flow out of the system and into the surroundings if it's not a perfect system. Okay. All right, so the surroundings could be other parts, okay, of the area. Okay, so everything else is considered to be the surroundings, okay, or the environment. Sorry, I underlined the wrong sentence there. Okay. All right, so there's 3 kinds of systems, and the 3 kinds of systems are based on whether energy and matter can move in and out of the system. Right, the most common type of system is an open system. Right, in an open system, both matter and energy are exchanged. Man, what is going on with this? All right, so an open system is one that exchanges matter and energy with its surroundings. All right, so it's completely exposed, right? And so it would be taking stuff in and then also putting different materials back out. Okay, a lawnmower is a good example of an open system. Okay, it takes oxygen from the surroundings. Combustion occurs within the lawnmower. It exchanges back to the surroundings carbon dioxide. So there's an exchange of matter with the surroundings. But as the lawnmower combusts the fuel, the lawnmower gets hot, and that heat energy goes to the surroundings as well. Okay, so it's exchanging both matter and energy with the surroundings. Okay. All right, and a closed system, okay, cannot exchange matter, but can exchange energy with its surroundings. So anything that is an airtight seal would be considered a closed system. All right, so if, let's say, you went grocery shopping, you bought some nice steaks, okay, you brought them home, you put them in a Ziploc bag and threw them in the freezer. Right, the Ziploc bag is a closed system. Matter is not getting into the Ziploc bag or out of the Ziploc bag. It's an airtight seal. However, as soon as you throw it in the freezer, the heat energy from the steak is being absorbed by the freezer, and the thing will eventually freeze solid. Right? Everybody kind of follow me on that? So anything that's an airtight seal, closed system. And lastly is an isolated system. that cannot exchange either matter or energy with its surroundings. It is virtually impossible to create a truly isolated system. Right? It's easy to create a closed system. We can seal something off airtight. That's easy. But to actually prevent all energy from flowing in or out of a system is virtually impossible. Okay? Even something like the International Space Station is not an isolated system. It still slowly bleeds away energy to the surroundings. In fact, it's not even really a closed system. Right? If you use the Space John, okay, it vents air to space in order for you to be able to go to the bathroom in zero gravity. Probably something you never thought about, but going to the bathroom in zero gravity is a lot different than going to the bathroom in real gravity. You kind of depend on gravity for things to fall away from you. Think about it. Okay, so what actually happens on the International Space Station is you sit down on the Space John and you turn it on and it gets, well, as the astronauts describe it, windy. Okay, because there's they just essentially open a small hole to space so that air is blown out in there and it just kind of pulls stuff with it, and then they collect all that stuff and they put it in a disposable capsule which they jettison later. Chris Hadfield said, the next time you see a shooting star, it might not be a meteor, it could be our poop comet. Well, because Earth's gravity will pull it in.
Yeah, but that would be really funny. You see, like,
well, it burns up though. It burns up in the atmosphere, right? As it re-enters. So yeah. So even the International Space Station is not an isolated system. It's not even really a closed system because they can vent it to space. Okay. Yeah, it's virtually impossible to create something that's perfectly isolated. Everything is going to have some amount of energy transfer. We can insulate things really well. Okay. I mean, you can build, coolers and stuff like that that can keep ice in them for days even, but eventually the ice melts. They're not completely isolated, right? So it's really difficult to do that. But we do a lot of our physics that we do in high school as though we're doing it in an isolated system. That way there's no energy lost to other things and it's easier to keep track of stuff. All right, questions on the three types of systems. That could be an easy multiple choice question. Okay, very easy. All right, first law of thermodynamics, and it says, and the law of conservation of energy. I like to scribble that out and say, is the law of conservation of energy, because it really, that's what it is. Okay, so basically the first law of thermodynamics tells us the ways in which we can change the energy of a system. Okay? Energy can't be created and it can't be destroyed, but I can change it. I can turn it from one type to another, or I can add it to a system, or I can take it away from a system. All right? If we're talking about thermal energy, then that's heat. I can add heat to a system, or I can have the system give heat away, or just have it go to the surroundings. Right? Or I can do work on a system that would add what kind of energy? Mechanical. Or the system can do work on something else, okay? And that would be a loss of mechanical energy from the system, but a gain of mechanical energy to whatever was being worked on. Everybody follow me there? Yeah? Okay, so the weird part of this would be, if I had a system that consisted of a ramp and a ball, okay, I let the ball go down the ramp, okay? Does the system lose energy when I do that? Actually, it doesn't. Okay, the system wouldn't lose energy because all I'm doing is converting potential energy into kinetic. I'm changing the kind of energy, okay, but the energy within that system would still be conserved. Okay, it would still be there in some shape or form. All right, so the big thing here is it's important to distinguish heat from work. Okay, work involves the movement of matter from one location to another. Okay, so that means mechanical energy. Okay, and so if we do work on something, okay, then we're adding energy to it. If it does work, then we're losing energy. Okay, everyone all right with that idea there? Okay. Now, heat is different. Okay, heat can flow, okay, through things. So if we're, it sounds weird, but you don't like, we say do work on a system, you don't do heat on a system. It's not, doesn't sound right to say it that way, but if I add heat to a system, I've added thermal energy, okay, to that system. All right, So this whole thing here about work being done says work done by a system on its surroundings is considered negative because the energy of the system will decrease. All right, so if I allow the system to do work on something else, the energy of the system decreases, but the energy of whatever it was working on increases. Again, it's all conserved. I'm not losing any energy anywhere. Okay, so the first law of thermodynamics is already kind of highlighted there in your notes. That's important. Okay, it is really just a restatement of the law of conservation of energy. It says that the total energy of a system, including heat, okay, remains constant. Whenever heat is added to the system, it can transform into equal amounts of some other form of energy. Okay, so it's talking about how a conversion of energy doesn't mean a loss. Okay, a conversion of energy just means a change. Anytime there's a change, that's fine. We're still conserving the energy. Okay, the rest of that's kind of what we just talked about, so we'll just move on from there. All right, now, how many people have heard of a perpetual motion machine before? Okay, possible to make one? No. Why not? Right, energy is always lost anytime there's an energy conversion. It's not destroyed, but it's turned into other forms of energy, and those forms of energy are not useful to keep the system going or the perpetual motion machine running. Okay, any machine when it's running makes noise. Okay, sound is a form of energy. Where does the sound come from? It comes from the conversion of mechanical energy into other forms. Okay, and as a result, energy is lost, and sooner or later, no matter how well you've designed that system, it's eventually going to stop because energy is going to be converted to other forms. Now, even if you could build a perpetual motion machine, would it be useful? No. Exactly. It would never do any useful work because as soon as it did work, it would lose energy and stop. Okay? A perpetual motion machine could only ever exist as a scientific curiosity. Right? It can't do anything but run, even if you could make one. Right? It could never do any useful work or it would stop. Right? So in that way, building a perpetual motion machine is basically useless.
My neighbor, he is an engineer who managed to build a machine after 30 years of trying, perpetual motion machine that actually.
That breaks the laws of thermodynamics. There has to be some input of energy into it.
To start it, there's an input, and then plug it into DC.
Okay, it can run, but it can't do work on anything else. If it did, it would be creating energy, which would break the laws of thermodynamics, right? It's got to get energy from somewhere, right? If it's going to do work, that it can't, otherwise it's creating energy, right? If I just say, all right, I'm not putting any more energy into this thing, but I'm going to make it do work, then I'm creating energy somehow. Okay? So there's something in there that's not truly perpetual. It's probably highly efficient, but not truly perpetual. Yeah? I know, because I've had someone bring that one up before. It's like this tubular thing with static discharges or something.
No, he's doing like Tesla thing, using some coils and other things that take energy out and back in, out and back in.
Right, but so it's going out and back in. So it's still being, it's still going back and forth, right? It's not going out permanently.
But there is a lot of discharge.
There's got to be something in there we're missing, but yeah. Okay, so perfect machines, like we say, would be called perpetual motion machines, but we can get close to that. But because every energy conversion results in the loss of some energy, because no energy conversion is 100% efficient, okay, some energy is always going to be lost. Okay, so the second law of thermodynamics is actually what forbids the production of a perpetual motion machine. Okay? The second law of thermodynamics says that energy always flows from a high energy object to a lower energy object. So if I've got this thing running, energy is going to flow out of it. Sound, heat, whatever. Okay, it's going to flow out of it and eventually it's going to stop. Okay, everybody follow me on that? Okay. So these are some ideas that people had. Like this one here is a bit ridiculous with the spinning wheel with the pie-shaped things. Okay, so the ball would come back to the middle and then as it got over to this side, it would roll to the outer edge and keep the ball turning. Okay, and then as it came back up this way, the ball would roll back into the middle and then roll over to the side here and keep it turning. Except that what would you hear all the time while this is running? The ball's rolling. It's just sound, which means it's losing energy, and it's eventually going to stop. Okay, this one I thought had like the most potential. Okay, because it uses a magnet. Now, eventually, though, magnets just demagnetize. Eventually, they stop being magnetic. But okay, if it was pulling this ball up to the top of the ramp and then it fell through the hole, okay, then it would come back down. But again, there's this point here. The ball has to open that door. Yeah, and you'd hear it drop. Yeah. Okay, but the ball has to open that door, and eventually it wouldn't, or eventually the magnet would stop. Okay, there's still going to be energy lost here. If I tried to make this thing do any work, it would stop. It wouldn't be able to keep doing it. Okay, a heat engine is a simple idea, more difficult in like producing it to actually do anything. But the idea is sound. If I can have a high energy area, okay, and a low energy area, heat will flow between the two, and it'll flow in only one direction. If I can place a machine in between the hot and cold, energy has to flow through it, and then I can make it do what? Work. All right. So the key to making this work is that the temperature difference has to be extreme. Right? It can't be like, oh, I've got a 20°C thing over here and it's 18 degrees over here. That's going to do a whole bunch of work because the energy is going to flow between the 20°C and the 18°C. There's hardly any energy flow there because there's very little difference between those. Okay, but in something like a jet engine, which is just a heat engine, okay, we're talking about the area where the jet fuel is burned being hundreds to maybe thousands of degrees Celsius, and then the surrounding air, which would be considerably cooler. All right, so heat would flow from the area where the energy is, where the fuel is being burned, through the turbines. Okay, that's basically just fancy fan blades. Okay, that would turn as a result of the heat taking air through. Okay, and forcing them to turn. Right, the more fuel you put in, the faster the blades will turn because the more energy will want to flow from hot to cold. The greater the difference you make, the higher the rate of flow is through the engine. All right, so if a plane wants to go faster, it burns more fuel. Okay? It just makes the front of the engine hotter so that air flows through the engine more quickly. Okay? That sort of makes sense? All right, so heat in a heat engine flows from a high temperature area to a low temperature area, and then that heat can be converted to mechanical energy. So that's how a heat engine works. Okay, we convert it to mechanical energy, which can then do work. But like we say, the key for this is that there has to be a big difference between the hot area and the cold area. Okay. In the internal combustion engine, the fuel in the combustion chamber burns at a very high temperature, okay, and that causes the gases inside the cylinder to expand rapidly. Right? So when you burn fuel, it gets really hot, it produces carbon dioxide gas that expands rapidly and pushes the piston down. Right, that's how an internal combustion engine works. So the gas explodes essentially, pushes the piston down, and then it cycles through until it can compress the gas again and ignite it. So it actually goes through 4 cycles. That's why a regular gasoline engine is known as a 4-stroke. Okay, there's the compression stroke where the gas and the air fuel mixture gets compressed. There's the ignition stroke. Then there's the relief stroke, and then there's the exhaust stroke. So there's an intake stroke, a compression stroke, a work stroke, and then an exhaust stroke, 4 strokes. Okay. What's that? A 2-stroke doesn't have to worry about the oil part of it. The lubricant is different in that. So in a 2-stroke, it fires every 2nd time, whereas in a 4-stroke, it only fires every 4th time. Yeah, it's weird, but it works slightly different. Essentially, the intake and exhaust are the same valve. 4-stroke. Yeah. Is more efficient. Yeah. Well, but in a 2-stroke, you have to mix the oil in with the fuel. Okay, and that's highly polluting, which is also why we've moved away from those. Okay, lots of older diesel ships were 2-stroke. They were 2-stroke diesels, and they would put like blue-black smoke out all the time. Okay, like if you ever seen, guys who drive those chipped diesel trucks, every time they step on the gas, this big black cloud comes out of the back. It's kind of like that. Yeah, and then they go about that far. Okay, so in the internal combustion engine, we're essentially using that. We're using heat to cause things to move around. We're turning heat into mechanical energy. Okay? It's just not a really efficient way to make mechanical energy, but it's the easiest way to make it. All right, so this was the design if you'll call it that, of the first heat engine. Okay, it was designed that, or it wasn't even actually ever manufactured. It was just kind of a thought experiment. Okay, the guy said, I'm going to have this turbine and I'm going to have it attached to two different water tanks. One water tank will have a short pipe that will be in the warm water near the surface of the ocean, and the other one will have this big long pipe that goes really far down into the ocean where the colder water is. And then the warm water will travel through the turbine, turn the turbine, which will propel the boat forward and over here into the cold water, and I'll create this cycle, which is ridiculous because the difference in temperature between the surface of the ocean and the deepest part of the ocean is not very large. Okay. Plus, this warm water and this cold water are already in contact with each other. What's the motivation to go through the turbine? Okay. They're already naturally cycling. So amongst other practical problems, having a ship that has a big long pipe dangling from the bottom of it is somewhat impractical when you start getting into shallower water. It starts to be a problem then because it drags and breaks. And then you have no propulsion. You're screwed. So yeah, it didn't really work, but the idea was there. Okay. All right, so heat engines and heat pumps. Okay, they work slightly different. Heat engine harnesses the second law of thermodynamics. It knows that you know, from hot to cold is the direction that energy is going to flow. A heat pump uses energy to go the other way, to reverse the flow. Right? So your refrigerator is a heat pump. Okay? Your air conditioner, if you have one, is a heat pump. Okay? It uses energy to force hot air or hot material into an already hot area. Okay? It's essentially active transport for energy. And we talked about active transport in Unit 2, where we're pumping stuff from a low concentration to high when everything naturally wants to go the other way. That's what a heat pump does, except it does it with energy. All right. So with a heat pump, okay, we're using mechanical energy to transfer heat. Okay. In your house, what thing uses more electrical energy than anything else? Your refrigerator and your air conditioner. Okay. They use more electrical energy than anything else in your house because they are trying to circumvent the second law of thermodynamics. They're trying to make energy go away it's not meant to go. All right. So heat engines, like we said, they can come in all types. As long as there's big differences in temperature, they will work, including this thermoelectric converter. Okay? If you had like a really hot beaker full of water and a really cold beaker full of water, and you had these copper bars that were in them, you could actually get the fan to spin. Okay? But it would only spin until, right, until that temperature differential gets, you know, close to nothing, right? Because eventually, obviously, the heat, you know, these just being beakers, the heat's also just naturally going to flow across, not necessarily always through the electric motor here. So when these start to get close to each other in temperature, the fan will slow down. In fact, it'll just gradually slow down the entire time because that energy differential is disappearing. The same is true for a battery. Okay. When we first use a battery's fine, it works great, okay? But as we use it and it gets to the point where we consider it to be dead, it's not really dead, it's just that the difference between the positive and negative parts of the battery has gotten so that it's not different enough for electrons to flow through the battery anymore. There's still energy in it, but there's not enough differential between the positive and negative to create a current, okay? That's also why you can test a battery to see whether it's good by dropping it. Anyone ever seen that? Okay, take like a AA battery, okay, and just hold it a little bit above. If you drop it and it stands up, it's good. No. Yeah, it's good. If it tips over, it's shot. Okay, because what happens is stuff starts to build up at the top. Okay, like material kind of transfers over, okay, to the top, and then as the battery is used, and so it gets heavier at the top. So when you drop it, it tips over. Okay, it's good if you drop it and it just stays going because the bottom's heavy. Yeah, it's weird, but it's true. Okay. All right. All right. So we talked about that. Okay. Now heat pumps. Okay. Heat pumps are different. So heat engines are simple. They harness the flow of energy from hot to cold. They're just using what naturally happens. But a heat pump is going to try and go the other way. So in your refrigerator, okay, at the bottom of the refrigerator is a compressor. Okay, that's the loud thing that you can hear running. Okay, so what happens in the compressor is it's taking the coolant, the refrigerant that runs through the refrigerator, and it's putting it under extreme pressure. Okay? When it does that, it turns that coolant from a gas into a liquid. Okay? When that happens, heat is given off. Now, where did that heat come from? Yeah, well, I mean, it was in the refrigerant, but the refrigerant picked it up from where? From the food inside your fridge. Okay, so the refrigerant circulates through the walls of your refrigerator and absorbs energy from the food inside. Okay, as it does that, it changes from a liquid to a gas. And then it flows down to the compressor, which forces it back into a liquid state. And when it does that, it gives off the thermal energy that it absorbed from your food. That has to be vented out, which is why when your fridge is running, warm air is coming out from the bottom of it. Okay, what you're feeling there is the energy that's been absorbed from the stuff inside the fridge. Okay, it's being vented back out into the hotter area. Okay, the natural flow of energy says heat should be going into the fridge. Okay, but the fridge is forcing that heat back out into the hotter area. Right? This is why you can't use your refrigerator as an air conditioner. Homer Simpson tried it once. Okay, you guys ever see the episode where they got air conditioning? Okay. He said, it came to me one night when I came down for a snack. I opened up the fridge and it was cold inside. You know, because it's Homer and he's stupid. Okay. So anyway, what he did is he left the door open and put a blanket over the open door to the refrigerator and just hung out with the door open inside this blanket. Except the blanket went like this and it touched the floor. So all the heat that was coming from Homer and going into the refrigerant was trying to be pumped back out into the same place. So what happened was he blew the compressor because the compressor was running constantly because it couldn't push the heat away because he had essentially made it try to heat or cool the whole house or that whole area. And it was trying to pump the hot air into the area that it was trying to cool. So it just ran constantly until it quit. Okay? That's why your air conditioner is on the outside of your house. Okay? It pulls air from inside the house into the compressor. Okay? It cools it by the same process your refrigerator uses, but then it blows the hot air outside and it blows the cold air back into the house. Okay, so it's separating the two. Yeah, that's why it takes so much energy. Usually the reason you're running your air conditioner is because it's bloody hot outside, right? It's trying to push that hot air from inside your house where it's only like 25 degrees outside where it's 30. Okay? It's going against the laws of thermodynamics, but okay, it can do that as long as it's using energy to do it. Okay? It's kind of cheating. All right, so those underlined parts there, guys, are the important stuff. Make sure you underline those as well. Okay, that's the stuff for heat pumps. Okay, I would like you guys to answer those questions there, just the circled ones. Okay, we'll be good. We'll talk about those here in a little bit. Okay, let's quickly talk about these ones here. So, first law of thermodynamics. First law of thermodynamics says energy can't be created or destroyed. It can be transferred. Okay, if you want to add energy, you do work on a system. Okay, if you want, it can also transfer energy away by doing work on something else. All right, distinction between work and heat. They're both transfers of energy, but they're different because. Right, one's a transfer of thermal energy, that's heat, and one's a transfer of matter, which is mechanical energy. Okay, that's work. All right. Identify whether each of the following is best explained by the first or second law of thermodynamics. A bouncing ball eventually comes to rest on the floor. Second law, okay, because it says that energy flows out from a high energy area. Okay, the ball would have high energy, but each time it hits the floor, sound is produced, the ball is deformed slightly. Okay, all of that kind of stuff, all resulting in energy flowing out from the ball to the surroundings. Okay, a metal spoon eventually becomes hot when placed in a pot of boiling water. Second law, okay? The heat's flowing from the boiling water and into the spoon, right? And then C, energy can't be created or destroyed, is obviously law 1, right? Okay, number 7, state the second law of thermodynamics. Energy flows from hot to cold, high to low, yeah. Okay, number 9, if you have a really cold drink, lots of ice in it, okay, you often will see water condensing on the outside of the glass. Which way is the heat flowing? Yeah, towards the ice, into the drink, okay? Because the surroundings are hotter, okay? The glass itself is quite cold, so water vapor in the air, when it touches it, condenses, okay? And as it does that, it actually transfers a lot of energy into the drink, okay? Water condensing onto something releases a lot of energy. Okay? That's why you have to be worried about like being burnt by steam versus by boiling water. Steam will burn you worse because it changes state from gas back to liquid and releases a lot of energy when it does that, okay? All right, and for number 10, which law of thermodynamics best describes the following, or is best explained by these statements? Okay, A, you can't get something for nothing. Yeah, law 1, energy can't be created or destroyed, so you can't get something for nothing. You can't even get close to getting something for nothing. Still, yeah, I'd say law 1, but I'd say you could probably make an argument for law 2 as well because energy is always flowing away. That's why you can't get close. Okay, a rock will never suddenly jump into the air. First law. That would involve the creation of energy and some sort of sentient rock. Yeah. Okay. All right, questions on any of those? All good with those? Okay, and I think that's where I cut your notes off, right? I didn't go further than that for this one. Okay, so this other stuff here, guys, is just kind of how we used our understanding, rudimentary as it was, of energy to develop technology. Okay, especially looking at like developing the steam engine, moving towards the internal combustion engine, things like that. Okay, we wanted to harness the ability to use heat to do work. Okay, we knew that relationship was there. We knew that when things got hot, they expanded, and if we could harness that expansion, it could do work. Okay, so the first idea on harnessing this was something known as the Gunpowder Engine. Okay, so Christian Huygens came up with this idea, okay, about the Gunpowder Engine. So basically, filled a container with gunpowder and blew it up. Okay, as they're rapidly expanding gases in an explosion. Yes, so it pushed the piston upward and did work. Big problem. Container destroyed. Piston can't reciprocate, which means it would only be used once. Okay, then you would have to reset the whole system and blow it up again. So while he proved that expanding gases could do mechanical work, beyond that, it wasn't really an effective type of engine. Okay, then we had the idea of the heat engine. Okay, the heat engine basically just used the natural flow of energy from hot to cold. Okay, the big thing here, guys, was yeah, we knew that that could happen, but we needed to build something that would reciprocate, that is reset itself and cycle through phases where it would do work, okay, versus phases where it was kind of being set up to do work, okay. And so that's where the reciprocating steam engine kind of comes into play here, right? The Savory engine, okay, was a type of engine that used, again, steam to do work. It would pump water, okay, from like mines and things like that out, but it didn't create enough pressure, okay. And kind of the limiting factor for early steam engines was making tight seals between the metal pieces, right? They didn't have, like, you know, the ability to manufacture thin rubber gaskets and things like that that would help them to create tight seals. So oftentimes these engines would be running, getting really hot, and then a seal would break, okay, or the metal wouldn't be tightly sealed, and hot steam would come shooting out of one part of the engine, and it could scald workers and things like that. And of course, once steam starts coming out of it, you lose all the pressure in the engine, and the engine doesn't do any work anymore. So it was really hard to build one that could do a lot of work because it involved building up a lot of pressure, and it was hard to get that. Okay. Having the idea of kind of having pulleys in there was kind of the first step toward getting a reciprocating engine. Okay, the Newcomen engine was one of those. Okay, it still used steam. The boiler could produce steam that forced a piston up in the cylinder. Okay, but in order to get it to reciprocate, what you had to do was throw cold water on it. Okay, so you'd get the boiler really, really hot. The steam would push the piston up, and then you were kind of stuck because there was no way to get the piston to come back down except to cool the whole thing off and make the water condense back into or the steam condense back to water and have the piston come back down. So not really efficient in that, okay, we got this big fire, we're heating up the boiler, we got the piston to move up, okay, now everybody throw cold water on it. Puts the fire out, you got to start all over again. Like, it wasn't really a practical thing. Okay, but Watt was kind of the first person to get this idea about the reciprocating engine. Okay, he noticed, he knew obviously there's a tremendous waste of heat if you're constantly heating and cooling the same container. Plus, heating and cooling a container rapidly usually causes it to what? Warp and crack, and then it doesn't seal properly anymore. Okay, so there were some major problems with that. Okay, so what he did is he reduced the amount of heat required to operate the engine and made it a bit more efficient. Okay, and essentially allowed it to become reciprocating shortly thereafter. Okay, all right. So the internal combustion engine started out a lot different than what we use today. Okay. The idea at first was to use like coal gas and things like that, but they were less stable, harder to get your hands on, stuff like that. So they had some definite drawbacks, okay? But it used coal gas ignited by an electric spark, which is essentially what we use today. We still use an electric spark to ignite the fuel, okay? So the difference between a steam engine and an internal combustion engine is that in an internal combustion engine, the combustion is inside the cylinder, whereas in a steam engine, the combustion is external. Okay, you burn the fuel outside of the boiler, you heat the boiler, and then the boiler does all the work after that. So the fire is outside, whereas in an internal combustion, it's inside. That means an internal combustion engine can be smaller. Okay, steam engines are by their nature very large. Okay, but an internal combustion engine can be a lot smaller. The problem is building one that could survive the constant explosions that happen in an internal combustion engine. That was kind of the stumbling block early on, and getting one that could be powerful. Okay, they had problems getting the engines to compress the fuel efficiently. Okay, the whole key to getting the ignition of fuel to do a lot of work is to have it highly compressed when you do it, right? And our engines will generally do that. Okay, more powerful engines typically are higher compression. Okay, most cars are somewhere on the nature of like 9-to-1 compression, okay, something like that. But high-end engines can be 11-to-1 or 12-to-1 compression. They're higher compression, so they push the fuel harder before it's sparked, and that leads to them generating more energy when the spark happens. Okay. All right, so this is what happens in an internal combustion. I was kind of explaining this before, okay, in a typical kind of 4-stroke type of engine. So the first stroke, okay, is the intake stroke. So as the piston is moving, this piston's moving down, and that causes the intake valve to open. What comes through the intake valve is the air-fuel mixture. Okay, air-fuel mixtures created in a number of different ways. If you have an engine that has a carburetor, which you probably don't because they haven't been around for a long time, okay, that used to mix the air and the fuel. Okay, modern cars will have a fuel injector, okay, that creates the air-fuel mixture through a fuel injection manifold. Okay, anyway, they get the fuel-air mixture and it comes in through the intake valve. It's drawn in because the piston moves down and essentially creates a vacuum that pulls the fuel in. Okay, then the piston will start rotating upwards, and when it does that, the intake valve closes. So now you've got an airtight condition where the piston is moving up and compressing the fuel. When it gets to the top of the stroke, the spark plug will ignite. So it just makes a little electrical arc that detonates the fuel. When the fuel detonates, that pushes the piston down. That's what we call the power stroke, okay? Because that's where the power is generated from that piston, okay? So it pushes the piston down, okay? That's the part where it drives your car, and then as other pistons fire, this piston will move back up again, but now the exhaust valve is open and the exhaust gases are pushed out through your exhaust system afterwards, okay? So 4 cycles of the motor in order for all of that to happen: intake, compression, power, exhaust. Okay, that's what has to happen for all of that. Okay, does that sort of make sense? Okay, that's how it works. Very simply, that's how it works. Obviously, there's more to it than that, but that's very simply how it works. Well, it depends on the type of vehicle you have. Most vehicles have now what's called an overhead cam, which is a rotating bar with different shapes on it. So as the engine cycles, these things will push on springs that open and close the valves based on what position the pistons for each cylinder are in, right? You don't have all cylinders firing at the same time, right? Yeah, they offset each other. Otherwise, yeah. Does that make sense? So a two-stroke engine will usually have less cylinders because it fires every second time, right? Whereas yes, the more cylinders there are, generally the more power there is because you have more displacement, right? You have more things moving. Okay, everybody kind of follow on how that works? Just because usually people ask. Okay. All right, so that was kind of the idea behind it, and then it went through a whole bunch of different variations and stuff before it became kind of a mass-produced type of vehicle. Okay, Henry Ford kind of being the first person to really make that work. All right, we're going to leave it at that for your exam tomorrow.